Good morning, everyone. See, do I have audio? Yes, I do. Okay. All right, getting situated. Sorry, I just got a phone call from my department coordinator. Gotta let him know I'm in class now. Woo, boy. We'll wait a couple minutes till everybody gets here. See, am I recording? Yes, I am recording. But we have some grading updates. Did everybody get their ECC email? It's like important news.
Yeah, the no harm grading.
Yep. So I want to take a couple minutes here at the beginning of class to talk about that. And then we'll do some homework questions, some 4.4 examples, talk a little bit about the schedule update. And yeah, so let's see. Well, usually we got a few more people here. So, and I know I started a little bit late, so we'll wait a couple minutes. Everybody get outside and enjoy the snow. Now we're supposed to get more today. Oh my gosh. Gross. My kids are usually like, they love the snow in winter, and they were, yeah, nope, not doing it, Dad. We're over it. It's just,
We did that. We tried walking and we got about a block away and my son's like, nope, not worth it. Can we go home now?
Yeah, we have a little hill on our property. It's like there's like a double property. The one next to it is like a drainage easement. So there's a little slope into the basin, and it's fun. I mean, they're getting a little big for it, but they still have fun, and they didn't even. We said, oh, you could go sledding one last time. No, not having it. All right, well, I don't want to wait too much time. We're recording it, so we'll just post the details too. So I'm going to pull up this email. I hope you got it. It should be in your student email. It's there's a bunch of updates here. I just want to focus on the ones that are relevant for us. So first, there is an extension for the withdrawal date, which I don't think is really relevant for anybody here. I think we're all doing okay, but this is true for all of your classes. You can withdraw up to, Wednesday, May 15th, like up to the last day of the semester, or whatever the last day for that course is, May 13th. You can withdraw on that date, and then it would just go in as a W. They're working on an updated refund policy. Normally, there's no refund for withdrawing this late. So there possibly might be a change to that as well. So the withdrawal dates are extended all the way to May 13th for if that's the last day of your course. Then there's a no harm grading policy, which is going to be relevant for us. You have to be really careful with this. But what this is, I'm going to just put in grades like I normally would. So after the semester's over, grade your finals. I'll put in the A, B, C, D, F like I normally would. After the semester is over and after you see your grades, you can choose to say, okay, you know what? I had an A or a B at midterm. I kind of lost it. I ended up with a C. That's all I need for my degree is like a credit for this course. This is especially true for like general education courses. You can just say, I'm going to call that credit. And it's not a grade, just call it credit. And then it doesn't affect your GPA. And it goes on your transcript. This is like people who take the AP test. They get credit for a class. They don't get a grade. They just get credit for it, and it counts for your graduation. You've completed the course. But one thing it might not count for, depending on where you're transferring to, is that might not count as a prereq for another class. So you have to really be careful about making that choice. And they're going to ask you to meet with an advisor if you're choosing the credit option, because it might not count. It'll still transfer as a credit course, but it might not count if you need Calc 1 for, like, say you're transferring you're all done here, you're headed to the U of I next year, and you need to take you wanted to take Calc 2 there. Most people would do all that here at ECC, but say you're going to do it there. They might not take that credit as counting as a C or better for Calc 2. So you do have to be careful with that. But you'll have all the way until June 4th to select that. There are no F grades this semester. So anyone who gets a failing grade in any course this semester, that'll automatically be converted to a no credit, and it has zero effect on your GPA. So there's no harm there. There will be no Fs. I think the Ds, you'll have the option to convert it to no credit. For some classes, a D might count for graduation. If it's not in your major, I don't know, there's some stuff there that is not usually applicable to math. But so you might want to leave the D. Otherwise, you can convert it to no credit if you like, you know what, I need that for the next class. A D is not any better than an F, and so I'll just call it no credit. But again, they're going to ask you to meet with an advisor to talk about that. It might be a digital meeting. Who knows what we're going to be under then. And so I think that, yeah, right. Yeah, so students will be required to speak with an academic advisor. And I think that's it. Yeah. Yep, for spring 2020 courses, you have until June 4th to use that. I think that's it. Yeah, does anyone have, I mean, I know about as much as you, because I got the same email, but does anybody have any questions? Maybe we can kind of talk about together about the grading, that no harm policy. Any questions about that? Okay. Feel free to email me. You know, we can try to figure out if you have any questions about that. But that's kind of nice. It gives you some options. So update today, what I want to do is go over homework questions if you have them. We have a quiz on 4.4 today. We didn't do the examples last time, so we can either do lots of homework questions or do examples. I need to get you an updated schedule, and that is my bad. I kind of dropped the ball on that, and so I didn't ask you to watch anything new for today, and I should have. We're going to skip a couple sections. We talked about this. Christopher asked last time if those are going to harm us for next semester, and I'm only going to do that for stuff that you could pick up on your own, or is just kind of a tangential topic and not a fundamental topic. So, because we really need to be into chapter 5 soon. So look for more info. I'm going to post an updated schedule soon about that. For next Tuesday, I would like you to watch 4.7. Oops, not 5.1, 4.7 and 4.8. 4.7 and 4.8. Watch those two for Tuesday. Right now, 4.7 is the only one posted. Dr. Sugar has all of these recorded. I just haven't linked them. But 4.8 I will also put in D2L. So that should be like an hour and a half's worth of stuff to watch for Tuesday, maybe 2 hours. I don't know. We'll see. I haven't looked at all of the timing on them, but it's 2 sections to watch for Tuesday. And then I really wish, because I know people have homework questions, and you know, we've been using our time here and that's great, but some people would really like to see us work through all the extra examples, and I don't know how to do both, and I can't meet, I'm sorry, I can't meet 4 days a week for an hour. I just don't have that time in my schedule at home anymore at home. So I really think that we can help each other more, and I would love to see people take a picture of 4.7 number 17 and post it and say, this is what I have. Does anybody have any ideas? And I'm usually on there and I can make a reply. Other people might see that. So I really would like to see more people use that. I think you're underestimating how valuable that could really be. So I want to encourage more people to post more homework questions there. Okay, all that said, I've got the 4.4 homework up here. Let's see, let me close this. And it's over here somewhere. There it is, 4.4. So let me get that homework up. And who would like to get us started with homework questions from section 4.4? I know we did a bunch last time, I think, but. Nick, go ahead, Nick.
I just had a quick question about next week. So are we looking at a potential exam for next Thursday then?
I don't That's tough. No, because I think we'll do an exam over chapter 4 and like 4.7 and 4.8 on Tuesday is kind of a short turnaround for you to then have the exam like on Thursday or something.
Okay.
Yeah, that feels like too short of a turnaround. I don't know. I'm not totally against it, but I feel like a little more lag time would be good. And then have it like, I mean, we could post it on Friday and you could have a couple of days to work on it. I could have a like Saturday deadline or something. That might be better. Just to give a little extra time to ask questions. So yeah, that's where like I need to have that schedule updated. So maybe we could post it. Yeah, maybe we could still have class on Thursday. And then we could have it posted after class and let's do that. So let's post the exam after class on Thursday. After class, what is that? It's 7 days, so the 23rd, and then have it due Friday.
Okay.
Yeah, that'll give you plenty of time. That should give you plenty of time to work on it. And that'll be chapter 4. And I'll be clear, there's some sections that we're skipping there. There's only 6 total sections. It's 4.1 through 4.4, and then 4.7 and 4.8. So it's just those 6 sections.
Got it.
Yep. Good question. Thanks for bringing that up, Nick.
Yeah.
How many sections do you still have to do for chapter 4?
We're going to do 6 total sections in chapter 4. We're going to do, let me get the table of contents here. We've already done 4.1 through 4.4. That's what we're working on today, 4.4. 4.5 is actually Calc 2. We're going to skip 4.6. And then 4.7 and 4.8 are the ones that we're going to continue to do. We're going to work. Those are the ones I wanted you to watch for Tuesday. So the next exam will cover 4.1 through 4.4, and then 4.7 and 4.8.
So on Tuesday, we will have a quiz on 4.7.
No
Quiz.
No quiz. So I don't know if you remember last time, like the last chapters, there's usually 1 or 2 sections at the end of this chapter that we don't have a quiz on, and they're just on the exam. So no quiz on those.
So we just have a exam directly on Friday, you said?
I'm going to post it on Thursday after class, a week from today, and then it will be due on Friday.
Oh, okay.
So you could turn it in on Thursday if you have a couple hours in, you want to knock it out, or you can wait until Friday.
So on Tuesday and Thursday, we have time to ask questions about homework and stuff like that.
Yeah, that's why I didn't want to do well, let's do it Thursday and not have class or something. Like, no, let's hold on. I want to make sure we have more time to ask questions. Exactly.
Okay.
Good.
So it'll be due Friday by midnight.
Yep.
Okay.
Yep. All right. Any additional? we're in the homework here. So, any other questions, or do you have a homework question from 4.4 that you wanted to ask? All right. I'm not seeing anything in the chat or hands raised. So let's do some examples then. That's actually, I don't know, kind of worried when nobody has questions, but it's kind of good because then we could do these examples. So I have these 4.4 examples. If you don't have them, they are, where did my page go? They are in D2L. There they are under the content. Under Unit 4, there is a 4.4 examples link, 4.4 examples. And so that's what I'm working on right now. All right, so let's do some 4.4 examples. Find all the relative extrema of this function. So relative extrema, those are going to be at the critical numbers. So let's go ahead and take a derivative. Polynomials are everybody's dream here. Always much easier to work with. What would that be? 20 halves. So 10x cubed, and then plus 40x squared. Convenient. Set that equal to 0. And It's algebra from there. Factor out a negative 5x squared. We get x squared minus 2x minus 8. And we can factor that quadratic into x minus 4 and x plus 2. Just this here. There we go. And then so we get x equals 0, x equals 4, and x equals negative 2. Now, at this point, if I'm trying to find whether there are relative extrema there, I have two options. Does anyone remember what my two options are to determine whether these are relative max, relative min, or neither?
You can make a chart and plug in numbers close to those in the.
Sorry, I think you got cut off at the end. What would I plug them into?
You can make a number line. So
Right.
since it's a polynomial, it'll be infinity, negative infinity to positive infinity, and plug those numbers onto that number line and pick numbers that are close to those numbers. So like for -2, you'd pick -3 or -1.
And what am I plugging them into though? That's the main question.
The derivative.
The derivative, right. So I could make a derivative chart. Yep, I could make a derivative chart. I've got -2, 0, 4, and then Christopher's right. We just pick some numbers like -3, -1, 1, 10, and plug those into the derivative. I'm going to use the factored version of it. It's always easier for me to use the factored version. It does not matter which version you use. But if I plug, let's see, I've got a -5, and then -3 squared will be a +9. -3 minus 4 will be -7. And then -3 plus 2 will be a -1. So I have three negatives multiplied together, so that's going to be negative. And the function is decreasing there. At -1, I have -5 still, and then a -1 squared is positive. -1 minus 4 is negative, and -1 plus 2 is positive. So all of that I will have positive. The function will be increasing. And at 1, again, -5, positive, and then 1 minus 4 is negative, 1 plus 2 is positive. So that one is also positive. Interesting. And then at 10, it would be -5, and then 10 squared is positive, 10 minus 4 positive, 10 plus 2 positive. So that will be negative and decreasing. So find all relative extrema. There would be a relative minimum at x equals -2 and a relative maximum at x equals 4. Now, the wording here is always a little unclear to me. Find all relative extrema. Like I located them, I know where they are. That's probably fine. If we wanted to know the actual relative minimum value, we would say, well, that the value is f of -2, whatever that is. Plug that in. It's just a function. You're calculus students, you know how to do that. And then the same thing for 4. So I'm okay if you said, like, I found them. It says find them. That's where they are. There's a relative minimum when x is -2. There's a relative maximum when x is 4. That's okay, but the actual relative maximum value would be the function. You know, if it says like what is the maximum value, then you would need to plug in 4 into the function. So that's the first derivative chart. That's one method that Christopher was talking about. Does anybody have any questions about that method or about the process we did there? Okay, so there is another option. I said there were two. So one option is a first derivative chart. So this is option 1, F prime chart. And so what is another option that we could do instead to try to answer the same question?
Is that the second derivative?
Correct. You could take the second derivative and we'll talk about what that tells us. So second derivative, negative 20x cubed plus 30x squared plus 80x. And then how do I use the second derivative? Well, back up. I'm sorry, Christopher. I'm sorry. I cut you off. What does the second derivative tell us?
If the second derivative is greater than 0, then you're going to have a relative minimum, and it's going to be vice versa for a relative maximum.
Yeah, the second derivative tells us concavity. So if it's concave up, it'll be a minimum. If it's concave down, then it'll be a maximum. So what we would do is we would actually plug in the actual critical values, the -2, the 0, and the 4. We don't have room for all of that, but let's do f double prime at -2. -20 times -2 cubed plus 30 times -2 squared plus 80 times -2. Let me see, can we do that in our heads? -2 cubed is -8. -8 times -20 is 160. And then 80 times -2 is -160. So those are opposites. And all we're left with is -2 squared is 4 times 3 is 120. So that's greater than 0. So it should be a relative minimum at -2. And yeah, that's what we got. It's a relative minimum. Relative minimum at x equals -2. This one, the directions did not say a strategy to use, so you could have used either one. If it doesn't say, you can pick whatever method you're more comfortable with. Be careful if it does say use a specific method, like use the first derivative test. That's the first one that Christopher told us, where you do a first derivative chart. If it says use the second derivative test, then you need to do the option 2. So just be sure to read those directions, and if they say a specific method, make sure you are actually using that method. Okay, any questions about this first example from the additional 4.4 examples?
I just have a quick question about option 2.
Mhm.
So if you were to do option 2 from the start, you'd have to set that one equal to 0 by itself, not right, and then get the critical numbers that way?
No, that's a really good question. So for looking for relative extrema, you're still going to need to set the first derivative equal to 0, because relative extrema occur at critical numbers, which are when the first derivative is equal to 0.
Okay.
So it would be like, let's kind of number the steps here. So the process you would do if you were going to do option 2, you would do, okay, I still need the first derivative. I still need to set the first derivative equal to 0. I still need to get those critical numbers. But then I would move over here, take the second derivative, evaluate the second derivative at those critical numbers, and then make my decision.
Got it. Okay.
Mm-hmm.
Thank you.
Yep. So relative extrema are all about those critical points, critical numbers. And so either way, you have to set the first derivative equal to 0. Mm-hmm. Good. Any other questions on that one? All right, let's do another one. This one is basically the same thing. Find and classify all the critical points. Just a little more challenging function this time. So we'll maybe just practice doing the first derivative chart again. One thing I'm noticing here is this makes me a little nervous with this radical. It's a cube root of something. So I guess I'm going to ask, like, are there domain issues? I have a cube root of something. Does anyone have any thoughts about, are there going to be limitations to my domain on this one? Are there?
The domain will be all real numbers.
Yeah, how'd you know that, Christopher?
A cube root is usually all real numbers because it has like an S curve, but also if you just take the cube root and turn it into a t to the second minus 4 power of 1 over 3, it's a polynomial. Well, not exactly a polynomial because it's not curved.
You got to be careful though, because I could do that for a fourth root, and I say, oh, hey, look, it's t squared minus 4 to the 1/4. But that one does have a restricted domain. So I think your memory of the cube root is better, like a better reason, where you can take the cube root of any number. F of x equals cube root of x has no restrictions. So that's actually correct. So we are not going to have any restricted domain. So the domain of the function is all real numbers. So we want to keep that in mind. If we get a place where the derivative doesn't exist, that's going to be important because the original function exists at all real numbers. Okay, so I actually am going to do Christopher's suggestion here because for me, it's easier to take derivatives with the fraction exponent. So we'll call it t squared minus 4 to the 1/3. And in our derivative then, we're going to have to use two derivative rules. How about somebody who hasn't answered yet today? Do you know what the two derivative rules are that we're going to use?
Product rule and chain rule.
Product rule and chain rule, yeah. Sorry, there's like, people are trying to like answer quickly and like multiple voices came at once. So product and chain rule is correct. So let's do the product. That would be 1 times t squared minus 4 to the 1/3 plus t times, and then here's where we need the chain rule, 1/3 t squared minus 4 to the negative 2/3 times 2t. And I want to pause there. Does everyone understand like where I got the negative 2/3 and where I got the 2t? Like, any questions so far? Okay, we're going to set this equal to 0. For me personally, I find it challenging to solve with the negative exponents. That's just a personal thing. So I'm going to rewrite anything with a negative exponent as a fraction. So I have t squared minus 4 to the 1/3. And then I'm going to rewrite this as 2t squared, because I have a t and a 2t, over, and then 3, because that's already in the denominator, t squared minus 4 to the 2/3, and that's all equal to 0. And that's just my personal preference. I find that easier to do. And then now you could clear the fraction, I guess. You could multiply both sides by the denominator, or you could subtract one term to the other side and then do it then. I don't know. I feel like that's going to be a little bit easier. I don't know. So I'm just going to arbitrarily choose to subtract the t squared minus 4 to the 1/3. And then I will multiply both sides by the 3 times t squared minus 4 to the 2/3. And it's interesting where this looks like this is going to just be ridiculous. And it ends up not being so ridiculous because you get 2t squared equals negative. And then I guess there's a 3 there, but then t squared minus 4 to the 1/3 and then 2/3, you add them together, that just gives you t squared minus 4. Who knew? Let's see here. So that's pretty simple to solve. Distribute the negative 3, add 3t squared, you get 5t squared equals 12. This is a little gross. T squared equals 12/5. So t equals plus or minus square root of 12/5. Your textbook, if this was in your textbook, they definitely rationalize that. It's not a huge deal. But square root of 12 is 2 square root of 3. And then you can rationalize it, square root of 5 over square root of 5. And so plus or minus 2 square root of 15 over 5 would be the rationalized version. Yeah, it's not a big deal. Those are not the only critical numbers though. Bad news for you. There are in fact 2 other critical numbers. So what have we not talked about yet?
Where G prime doesn't exist.
That's correct. Let's go up here. And whenever you have a fraction, that's like a red flag. Oh, there's a fraction. Is there a space where the denominator is 0? So G prime of t does not exist when, and I'm gonna like drew a little red box around it, when this denominator part is equal to 0. So that's when, in fact, it's just when t squared minus 4 is equal to 0. The fact that it's raised to the 2/3 and there's a 3 multiplied in front is really irrelevant. It's just when is that inside part equal to 0. So t equals plus or minus 2. So we actually, boy, this is messy. We have four critical numbers. Okay, I think what I'm going to do is I'm going to do a number line, and then I'm going to set up a calculator so that I can quickly evaluate the derivatives. I'll show you how I would do that. Ooh, I got to figure out which one is smaller. I think -2 is smaller than -2 because square root of 25 would be 5. Yeah, right? Why am I doing it on my phone? I can do it in front of you. Oops. Let's see here. So 2 square root of 15 over 5, right? 1.5. Okay. Oh, that's going to be annoying trying to find something in the middle there. -2 square root of 15 over 5. 2 square root of 15 over 5, and 2. Super annoying. Okay, so instead of plugging these all in by hand, I'm going to do this in Desmos, show you how to do this in Desmos. We're just going to write a function and then evaluate the function at all of those. So we'll do like a -10. I think this was that -1.5 something? So maybe -1.6, 0, 1.6, and 10. So what I'm going to do is in Desmos, I am going to type my function, I'll call it f of x, but I'm going to type in the derivative. So I have to look up at that again. Let's see if I can remember that. Unlikely. Okay, so I'm going to write a function, f of x equals, and I already forgot, 2t, or we don't want t, sorry, x squared minus 4 to the 1/3. And then plus 2t divided by 3. Oh, I'm just keep doing t's. You could do t's, but I'm gonna do x's. X squared minus 4 to the 2/3. Okay, let me just make sure that I did that correctly. 2t squared. Nope, this should be squared. Okay, does that look right? Squared minus 4 to the 1/3 plus, yeah, okay. Okay, I think we're good. Incidentally, check this out. If I graph x equals -2, look, my derivative does not exist there. And if I graph x equal +2, derivative does not exist there. That's good. Where are the funky 2 square root of 15 over 5s? Where are they on this blue graph? Think of what this is a graph of. They're on here. Watch this. Why did that work? Why is that point right there?
Because those are the points where the horizontal is 0. There's a horizontal tangent line there.
Horizontal tangent line, yeah, it's where the derivative was 0. And we were graphing the derivative. Yeah. So what I'm going to do now is I have this function. I don't really need the graph of it, but I have this function. And now I can do f at, didn't we say negative 10? F at, what was it, negative 1.6, f at 0, f at 1.6, and then f at 10. So I have this function, and then I don't have to type all these crazy numbers in the calculator every time. I can just use the function notation. So it just simplifies my life here. So it looks like positive, positive, negative, positive, positive. Okay. Positive, positive, negative, positive, positive. This is my chart. So increasing, increasing, decreasing, increasing, increasing. You can do that on your calculator as well. It's way more tedious, and Desmos is better, and you should use Desmos. But if you're interested, maybe just email me and I can show you how to do that on your calculator too. But we're at home. We have computers and phones that can use Desmos. Let's use the better tool since we have access to it. Why not? It's funny, some of this stuff has been like, man, I'm trusting my students to do this at home. Why can't I just trust them to use Desmos on their phones during a test? Like, why not? So now I'm thinking in the fall, or whenever we eventually go back, hopefully in the fall, like, I might just let my students use their phones and just say, just have Desmos open and use that. Okay, so it looks like increasing before -2, increasing after -2, and then decreasing. So it looks like we have a relative maximum at x equals -2 square root of 15 over 5. And then we're decreasing and increasing. So a relative minimum at x equals 2 square root of 15 over 5. And then something weird is happening at -2 and 2. I really want to draw the graph. That's really weird. It's increasing before and increasing after, but the derivative doesn't exist there. So usually I think of cusps like, oh, decreasing before and then increasing after, and the derivative doesn't exist here. But this one's increasing before and increasing after. Oops, I accidentally started some software with my finger there. Stop. Let's go back to Desmos and let's see if we can figure out what's happening. I think I know what's happening. Hopefully you have an idea as well. Close that. Close it. Okay, so let's graph the original function. F, or what was it, g of t equals, and then it was t times, and I'm just going to write it t squared minus 4 to the 1/3. And then let me take off my blue function there. And that point. Whoa. That is the weirdest looking. It almost looks like a cubic function, but weird. So what's happening at -2 and 2? How is it increasing before and increasing after, but yet they're critical numbers? What is that?
Slopes are still positive, but it doesn't exist.
Yeah, why doesn't the derivative exist there? It's positive before.
Vertical line.
Yeah, it's a vertical tangent line. I don't know if you remember way back at the beginning when we talked about derivatives, we could say, well, it doesn't exist at a cusp or a vertical tangent line. We don't do a lot of those because they're weird functions like this, is when you have vertical tangent lines. But yeah, there's a vertical tangent line there. And so that's what's happening at -2 and 2. At -2 and 2, there is a vertical tangent line there. Interesting. The downside is the only way to get those like really interesting functions is they're weird and the derivatives are harder. So you're not always going to be polynomials. You know, I mean, I'm sorry. It's not all going to be polynomials, but there, you know, this is definitely a more advanced one, and it's not like you're going to have a test full of these either. But when we get to our next test, you'll probably have one like this, something like this, where the derivative is a little more challenging, and then you get a little more. You have to really demonstrate a little more understanding because they're not as easy as the polynomial ones. But we'll have some polynomials for sure. Yeah, for sure. Okay, I think that's it. We were just supposed to find and classify all the critical points, and that's what we have done. Does anyone have any questions about this second example in our 4.4 example sheet here?
I have a question.
Yes, Haley.
If we had to write like the intervals for where it was increasing and decreasing, would we include the -2, or would we have to write two separate intervals for that?
Yeah, that one we would still include it because, so let me just say, so f is increasing. Everybody remembers these, right, where you had to write the intervals where it's increasing. So suppose it was that. We would say it's increasing on that. The reason we would say that is if x is less than -2, the function f of x is going to be less than f of -2. And similarly, if x is greater than -2, f of -2 will be less than f of x. What I mean is on the graph, if I pick an x value to the left, the y is going to be less than 0. And if I pick an x value to the right, the y is going to be greater than 0. So any number to the right of -2, the function is going up, and any number to the left, the function is going down. Even though the derivative doesn't exist there, it's still increasing through that point. So we would include it. Is that okay?
Yes.
Good. Any additional questions on this example? Okay, I'm not seeing any additional ones. Let's see what we have left here. Oh, this is gonna mess with your head here. This is good. I like this question. Not that I like to mess with your head, but I like this question because we got to think a little more carefully. We kind of just did this, but here we're given the graph of f prime. By the way, I wrote this question, and you can see I wrote it before I discovered Desmos. This is an old question. So this is not the graph of f. This is important. This is not the graph of f. This is the graph of the derivative. And so the question is, identify the intervals where the function is increasing or decreasing and where it has relative extrema. So in general, how do we determine where a function is increasing or decreasing?
If its slope is positive or negative.
Okay, so slope, positive or negative. And so we really need a first derivative chart, right? We need a first derivative chart. We need to know when is the first derivative positive, when is the first derivative negative. When we did these problems, we did one earlier. What's the first thing that we did?
We found the critical points.
Right? And that's when the derivative is 0 or doesn't exist. So you can actually look at those from the picture. So don't say it out loud. Why don't you take 15 seconds, and I'll give you a hint. There should be 2 of them. Can you find the critical numbers? So take 15 seconds, see if you can write those down. All right, how about somebody who hasn't answered yet today? Do you know what they are, what those critical numbers are? Yeah, Juan, why don't you go ahead, Juan? I can unmute you here. Oh, I can't unmute you. There
Is
you
it
go.
1 and 3?
Yeah, exactly. Yep, exactly. They're right here. F prime equals 0 at those points. Yeah, so that's 1 and 3. And so now we need to know, where is the derivative, positive or negative? Well, if we look over here to the left of 1, here f prime is greater than 0. So the function must be increasing. And you see how it kind of messes with you? The function is increasing, but you're looking at the graph and you're like, but it's decreasing. But the graph is not a graph of the function. The graph is the graph of the derivative. So the slope here, the slope is positive because this is a graph of the slope. And then between 1 and 3, you can see f prime is negative there. So the original graph is decreasing. And then after 3, f prime is positive. And so the original function is increasing. So f is increasing from negative infinity to 1 and from 3 to infinity, and decreasing on the interval from 1 to 3. And there is a relative maximum at x equal 1 and a relative minimum at x equal to 3. We don't know what the minimum value is and the maximum value. We don't, because we don't have the original function. So we can't actually find them, but we can locate them. We can say, well, it has a relative maximum when x is 1.
I have a question.
Yeah, go ahead, Sandra.
We say that before 1, the slope is positive. Is it because it's above the x-axis? Oh, okay.
Yes. Yep. That's why this one is, I don't know. For me, I just feel like this is really hard for students. And I think that's understandable because you're so used to looking at the visual and saying, oh, it's decreasing. But you're right. This is a graph of the derivative. And so I need to know, is it above the x-axis positive, below the x-axis
okay.
negative? Yep. Good. Anybody else?
Okay, I'm sorry. Could you, the relative max at x equals 1 and the relative min at x equals 3, how do you know? Like, I think I'm looking at it backwards.
Right. So the key is I'm looking at the first derivative chart, and it tells me that it's going up before 1 and then down after 1. So there has to be a maximum when x is 1. Okay. All right. Excellent. Any additional questions? Yeah, go ahead, Albert.
Does this mean that the original function has a relative max at 1 and relative min at 3?
Yes. Yeah, and we don't know what the original function is. We're actually going to learn how to kind of work backwards at the end of this chapter, and then that's what chapter 5 is actually all about, is starting with the derivative and working backwards. But yeah, we don't know what the original function is, but we do know it has a relative maximum when x is 1 and a relative minimum when x is 3. Yep, all of these facts are all about the function f, which we don't have. We have f prime. But all these facts are about the original function, the unknown original function. Good questions. What else? Any other questions? All right, excellent. I think we just have one more. Oh, we have a couple more. Let's see here. Concave upward, concave downward. Let's do example 5. This one is actually from your homework, and interesting, But I don't mean from your, I don't know if it's in your assignment set, but it's one of the problems. I feel like it's one of the problems, maybe not. It's similar to some you had in the homework, where we're gonna do a lot of stuff here. We're gonna find out where it's increasing or decreasing, so first derivative. We're gonna find out concavity, so second derivative. Points of inflection, second derivative. And then we're going to sketch the graph, which is actually all about 4.6, but there's a little bit of dabbling in it in 4.4 already anyway, which is why I'm not super concerned about having a whole section devoted to it. If we have to cut something, that's a good section to skip if we have to. So I think what I'm going to do is just dive right in here. If I want to know increasing, decreasing, just like we did for the earlier examples, we'll take some derivatives, find critical points, first derivative chart, all that. So let's see here. We get 3x to the fourth minus 12x squared. Let's find the critical point, set that equal to 0. We got some convenient factoring here. 3x squared factors out. X squared minus 4 is equal to 0. And so we get x is equal to 2 and 0, and then x is equal to positive or negative 2. I don't know, you've probably discovered this by now, but polynomials are a calculus student's best friend, right? Everything's easier with polynomials. So we have negative 2, 0, and 2, and let's put in like negative 10, negative 1, 1, 10. I don't know if anyone's been looking at the way your book does this. I feel like they make do they make like a table? Don't they make a table for theirs? I don't know. I just like the visual. I feel like the visual is better for me. Let's see here. Can we do these in our head? Negative 10. I'm not going to write all this out, but here's what I'm doing. Here's I'm plugging them in the factored version. I'll just write out the first one. So we're plugging in negative 10 in for all the x's. So positive, positive. So it's increasing before negative 2. When we plug in negative 1, it'll be the negative 1 squared minus 4 will be negative. And then same thing for 1. And then at 10, everything will be positive. So you can double check those if you want. What I'm doing there is I'm plugging those into the derivative. And we're just a little short on time. So I'm gonna just kind of breeze over that, but that's how I filled out the rest of this chart, just did it mentally in my head. And you can do that if you want as a student. It's just a little risky to do stuff in your head if you make a mistake. For me, it's not as risky because I have 10 people watching me, and one of you will catch it if I make a mistake. You don't have that option when you're doing a quiz or a test. All right, so we were supposed to find where it's increasing or decreasing, so let's go and answer that. F is increasing on negative infinity to negative 2 and 2 to infinity. And then kind of to Haley's earlier point, and she posted this in the Discord chat as well about concavity. It's here again, we would include 0 because it's decreasing, kind of flattens out, but then keeps decreasing. So technically it's decreasing all the way from negative 2 to 2. Okay. Any questions so far about the first derivative? Okay, I'm not seeing any. Let's do concavity then. Let's look at the second derivative. 12x cubed minus 24x, another simple one. Factor out 12x, and we get a little funkier this time. We get x equals 0, and then x equals plus or minus square root of 2. We're going to basically repeat the process, but now we'll be looking at the second derivative. So this doesn't tell us increasing or decreasing. This tells us the curve, the shape of the curve. Negative square root of 2, 0, and square root of 2. I'm going to do my old friend -10, -1, 1, and 10. And we're going to plug these in the derivative. So f double prime of -10. Sorry, we're going to plug them in the second derivative. 12 times -10 times -10 squared minus 2. Looks like negative, positive. So the whole thing's negative, and that means it's curved downward, concave downward. Doesn't mean it's decreasing. Now this is concavity, so it's curving downward. F double prime at -1 will be 12 times -1 times -1 squared minus 2. That'll be negative times a negative, so that'll be positive, concave up. And if we continue, you can check these on your own, but if we continue, the next one will be negative, and then at 10, it'll be positive. Be careful, it doesn't always alternate like this, even on polynomials. We saw one earlier where it didn't always alternate, so be careful for that. Sometimes it does, often it does, but it doesn't always alternate.
Is the curve supposed to be up or down? I think they got that backwards.
Donut point.
Yeah, he got out of the donut points.
I don't know, like I don't know how to deliver donuts to everybody. I don't know.
Uber Eats.
Right?
Yes.
that would be an expensive order. I need to order 28 donuts, individual donuts delivered to 28 different addresses. Oh my gosh. Okay. We did not leave nearly enough space because we're supposed to talk about graphing it here. So we'll see, but we can talk about concavity. F is concave down on, let's see here, -infinity to negative square root of 2 and 0 to square root of 2. And F is concave upward from negative square root of 2 to 0 and square root of 2 to infinity. Does the function f have any inflection points? Oh, Albert, sorry, I just saw your hand. Go ahead.
Sorry, I forgot. Like, what if you plug those numbers back into the original function?
The negative square root of 2 is 0 square root of 2.
Oh, no, like -10, -1, 1, and 10.
Those are not going to be helpful. They're just going to give you the function values, but they won't tell you the curve. So you want to plug them into whatever chart you're making. If you're making a first derivative chart, you plug them into the first derivative. If you're making a second derivative chart.
So you only use the second derivative to determine concavity.
Correct.
Okay.
That is correct. Yep. So I was asking earlier about inflection points. Do we have any inflection points here?
Yes.
Christopher, can you tell us more about them and how you know and where they are?
Inflection points is where you have an opposite sign. So there will be an inflection point at each one of these critical points.
Yep. Yeah, they feel like critical points. They're not called critical points because technically critical points are first derivative. It's the same idea though for the second derivative. I can't think of a name for them. For me, I think of them as possible inflection points where the second derivative is 0. You don't know if they're inflection points until you make the chart, and in fact they are. Whoa, that was a mistake. I'm just trying to scroll down here. So here's my question. We do have inflection points at x equals negative square root of 2, 0, and square root of 2. We also have some critical points over there. We have relative maximum. We have where it flattens out. We have this point at 2. If I wanted to graph it, I would need actual points for all of those. I would need points for all of those. And so I don't have nearly enough space here. I'm going to just cross off example 6 because we're not going to get to that. We did do a second derivative test earlier, so we did talk about that idea at least. So what I'm saying is if we're going to graph it, we need points. And so we need the critical points, -2, whatever goes with that, 0, whatever goes with that, and 2, whatever goes with that. It was 2, right? Sorry, yeah, 2. So we need -2 and 2. We also need inflection points, -√2, whatever goes with that. And then 0 we already had, so we don't need to do it again. We already have it. And then √2 and 0. We need all of those points. So how would I get all of those points?
Plug them back into the original function.
Right, and you know how I'm going to do it. And this is why the graphing is going to seem a little silly. I need a new blank graph. So I'm going to type in my function. And this is why the graphing is a little silly, because I'm going to type in my function so that I can plug in all those x values. But if I can type in my function, it's just going to graph it for me. And then I have the graph. So why do I need, why is this something that's worth doing? Asking you to use calculus to sketch the graph when you can just use Desmos. +2. And you can see those points there. It's really hard to see. I don't know if you can see them. So if we do f of -2, that's 14.8. So if I do -2, 14.8, you'll see that peak up there, right? That's the relative maximum. If we do, in fact, let me just do it this way, 2 f of 2. That's down here. You can hover your point. There's -10.8. If we do 0 f of 0, that one's easy to do, that's 2. And then the √2 ones are harder. They're not going to be very pretty. √2 f of √2. You can see that right there, and that's a little harder to see. I'm going to change my window here. I'm going to change my x-axis, just the x. I want to spread it out a little bit. I see your hand, Albert. I'll be there in a second. Yeah, maybe -5 to 5. Yeah, so then I can think we can see a little bit more what's going on. Go ahead, Albert.
As an answer, the inflection point should be a coordinate, technically, right?
Yeah, the inflection points. So it's all about, it's a little hazy about what is it asking for. If
Because
it asks,
isn't like the inflection point is where it, like where the derivative changes, right? So it has to be a coordinate, not just the critical point.
yeah, well, so there's just some length. You're fine. You're right. I don't even like calling the -2, 0, and 2 critical points, because to me they should be called critical numbers. Because to your point, if I want to use the word point, then it should be ordered pair, like a point, like an x and a y. And so it's kind of the same thing for inflection points. Do we mean, is it the x values, or do we mean the actual points? If you say, what are the inflection points, that's different than saying, where do the inflection points happen? So we just kind of answered where they are, but not what they are. So the what would be -√2 and then whatever f of -√2 is. So you're exactly right. You're fine. I don't want us to stress about it too much right now. But actual inflection points, you're right, would be the actual point. And I want to get back to your point about what they are. So here's this inflection point. You can see it kind of has some weird coordinates. It's not exactly -5.92. But I want to know, like, what's happening there? Why is that called an inflection point? This is really the point that I wanted to get to today. We're going to have to end pretty soon here. I know you have other obligations. So does anyone have a good, maybe can you do the raise your hand so not everybody jumps at once? Does anyone have a good explanation for why is it called an inflection point? What's actually happening there?
That's a change in the concavity.
Mm-hmm. Yep. It's a change in the concavity. I'm gonna see, can I draw over this? Oh, I can draw over the top of this. So cool. Okay, not as easy as the other one, but this is concave down here. You see the curve, concave down, and then it switches. I am so excited. This is the coolest thing ever. Now it's concave up. This is in Zoom, actually. Zoom lets me draw over whatever I'm sharing. So concave down to concave up. That's that inflection point. So yeah, that's what's happening there, because Albert was talking about the derivative changing. Notice that the derivative is negative for all of that. What's happening is that the derivative was increasing here. It was getting steeper and steeper and steeper. And then at this point, it started getting less steep. So the derivative, the change in the derivative changed there. It went from increasing, getting steeper and steeper, to then decreasing. There's another one over here, somewhere about right here. And that the same thing happened over there. And then the same thing happens at 0. The derivative was getting less and less negative, and then became more and more negative. And that's what was happening there. So there are 3 inflection points on here. And I think we talked about this last time about, you know, maybe a good question would be to give you a graph and ask you to point out what are the inflection points on the graph. And so I think this is useful for us to kind of talk about. I mean, we didn't actually draw the graph just because we had, oops, I have to erase my, clear my annotation, clear all drawings. There we go. Because we had the, this is why the graphing 4.6 is not really useful anymore, because you have technology. So what's more useful is kind of interpreting the graph, knowing when a function is increasing, knowing when the slope is increasing. It's concave up, that means the slope is increasing. And so those things are valuable to know. And so those questions we will definitely have. But I think we need to call it a day here. I think it should have popped up. It accidentally popped up this morning, but it should pop up again now. If you log into D2L, there should be a quiz there from some even numbered homework problems from section 4.4. That one will be due tonight. Yeah, and then let's go back, remind you what we wanted you to work on. Oh, sorry, I need to turn off the annotations. That was so cool though.
I have a quick question.
Go ahead, Christopher.
To graph the function, do you necessarily need the concavities? Couldn't you just use the first derivative points?
You know, when they're polynomials, yes. But the reason I'm hesitating is, let's suppose you have a relative minimum here and a relative maximum over here. You know it's going to curve like this and it's going to curve like this. What you don't know is where does it switch, right? Where is that inflection point? So to get that curve exactly right, you do need to know the location of that inflection point just so you can get the curve correct. So it is necessary, but you'd still be able to get the general idea. To your point, if you have the relative min and you have the relative max, I mean, you know they have to connect, you know, so it just, to get it precisely, you do need that inflection point, and it's all about the shape of the curve.
Thank you.
Mm-hmm. Mm-hmm. Any other questions before we call it a day? Oh, I was going to go back up to the schedule. Yeah. Okay. All right. I think then what I will do is I'm going to make sure to get links posted for 4.7 and 4.8. and kind of, my priority is to get you an updated schedule. That's on my list. It's on my list with an exclamation point on it. Do you see? Update schedule. And it has an exclamation point on it. So that's number one on my list, is to get you an updated schedule so you know what to expect for the rest of the semester. That's something I should have done already. So I will get that for you. And then you'll have 2 sections worth of videos to watch for Tuesday. And then we will have an exam next week, but we'll have class Tuesday and Thursday. The exam will be posted after class on Thursday and be due by the end of the day on Friday. Okay, you know the drill. Email me if you have any questions. Post to the Discord chat if you have some homework related questions. We'll talk again soon. Okay, take care, everybody.